last section, we used electrical energy to donate the electrons. That's what gives the electrons to use the electrolytic cells. In this one, we are going to do some large scale work. We are going to do things like refining. Okay, this is the one. The next one we're going to look at is refining, purifying, okay, electrowinning. Doesn't matter what you like. Refining, we want highly pure metals. We want very pure metal, very pure copper, nickel, gold, silver. We want very, very pure. Why? Well, because we want to use it inside here for our circuits, etc. We don't want to pack anything in there that could interfere in any way with it, because we're using very, very small voltages and very, very tiny currents. Milliamps are going through the calculators. Watches, things like this, right? It's very, very small currents that are used. So we want very pure material. Now, have you ever thought about when we mine something, okay? When we mine the material, all right? We mine it, that looks like mince. And somebody's definitely going to say, I minced it. No, I'm afraid I mined it. Mined. We mine the material. We get an ore. An ore generally is an oxide. Okay? Oxide, dioxides, whatever, right? But we're getting an oxides. We could also be getting a carbonate. Right? We could also be getting sulfates, but we are generally getting stuff stuck to other stuff. So we're getting contaminated. We're not getting pure copper out the ground, so we have to purify it. So how do we purify it? We have got an impure, or sometimes called a dirty ingot. Oops. Right? So let us just take copper as an example, shall we? What have we got? We have got this dirty great block of dirty copper. I'm saying dirty in a sense because it could have rubbish with it, all right? We've crushed it, we've washed it, we've done other processes on it, but we've still got other rubbish in there. So what do? I put it into my pot, all right? I should really take up cooking. Right? And I say, all right, I'm going to connect you to a fairly nice power source, and I'm going to, on this side, have another electrode. This is my dirty copper. This is my pure copper over here. Right? Why? What do I want? I actually want only to plate out. Our objective is to only plate out pure copper. That's what we want. This is the product of this reaction, is it not? The product of this reaction is to find pure copper. That's what we want. We've got dirty copper on that side. We want pure copper on this side. So if I want pure copper, what has to happen here? Well, this has to be where the copper plus 2 plus the 2 electrons form Cu solid. Is that not so? And where does that come from? It comes from here. Okay? This is copper solid is actually dissolving to give us the copper plus 2 electrons. So the copper plus is going this side. This must be my negative, positive. This is gain. This is reduction. Therefore, it must be my cathode. Right? I didn't have to work that out. This is my oxidation. Therefore, it must be the anode. Okay, so I can go and I can say this is my anode. This is our cathode here. Okay, let me write it up here. This is the cathodic side, the cathode on that side. And this is my... Okay, now what is this stuff? Remember, we need an electrolyte. This is our electrolyte. Okay, electrolyte. And what do I use? I use copper sulfate. Okay, we use some copper sulfate in here. And what do we get? We get pure copper coming out on the other side, because copper sulfate has got copper plus 2, SO4 minus 2 ions in it. Therefore, the copper plus 2 is going this way. All right. This side, the sulfate, but over here, this is the copper is coming out first. It's dissolving. Well, there we go. That's what we do. That's electrowinning. So anyway, at the end of the reaction, what have we got left? The rubbish. So we say, okay, what's left is this side pure copper, and that side is the rubbish that we don't want. Cool. So any metal we wish to purify, you're having to go through the same process. If they ask you, how would you do nickel? You've got your anode, which is your dirty one, your pure one's that side. You can work it out, because this here is what you want to happen. Is it not? That's what you want to happen. Straightforward, easy. You didn't even have to remember a single thing more than the first lecture that we did together. Next one, we're going to look at chlorine production. Let's look at another industrial process, production of chlorine. Production of chlorine. Okay, in other words, Cl. Let's say Cl2 gas. You could produce chlorine in different forms. But let's say we're trying to do, okay? What do we want chlorine for? Chlorine is in many things. Bleachers. We use chlorine in the swimming pools. So chlorine is a thing that we're going to be putting into lots and lots of stuff. Okay, so it's an industrial chemical which is very sought after. Right, so what do? Well, logically, what would we use? Hang on. Logically, we would use sodium chloride. Oh yeah, NaCl, solid. Why? Because it is salt. And why? Because there's lots of it. Okay, it's cheap. Where can I get it? Seawater. How do I do it? I put it into evaporation pans. All right. So I get salt. But hold on. We said that if we put salt in water and put electrodes in it, we don't get sodium, we get chlorine. But in this case, I want to say, but hang on, I want to get the sodium chloride. That's going to be a different method. Let us first look at this situation. Right? Over here. That is very frustrating when it does that. So essentially we will look at, so let's look at step 1. We want 2 Cl minus ions going to Cl2 gas plus 2 electrons. This is the oxidation, is it not? Therefore, this is going to be the anode of this chemical reaction. There it is, balanced out. You will find this in the table, in the half reactions. You've seen it before a dozen times. The other side, you get 2H2O plus 2 electrons going to H2 plus 2OH minus. Right. So what is happening here? That's the oxidation at the anode, right? This is reduction at the cathode. Remember, we get hydrogen gas given off. Why? Because sodium is the metal above. So sodium doesn't come out of this. But what have I got? We have got in there, we have got Na plus ions. And the Na plus ions were connected to the Cl. The Cl is gone. So where do they go? They go and we form NaOH. I am going to write the reaction down now. The actual reaction, if you go, you will find 2 NaCl, okay, plus 2 H2O going to 2 NaOH, right, aqueous, plus Cl2 gas plus H2 gas. Remember, at the bottom end, chlorine comes out before oxygen. So we are cool at the bottom end. It's a halogen will be produced before the oxygen. We've sorted that. At the upper limit, the sodium doesn't come out. What happens is the sodium in this cell, all right, in the mercury cell, which is part of the theory that you're going to have to look at. I'm not going to go through those in detail. What you got in the mercury amalgam is the sodium comes out into the mercury, which becomes, it's an amalgam of sodium and mercury, and the sodium can then go and be processed off. So in this case, what do we get? We've then got, okay. Now, let's just look at a problem here. All right. Can you see that we've got H2 plus Cl2, both gases? Okay. Now, this is not really a great reaction to have because it is highly exothermic. Can you see these two gases here are both given off in this reaction? So it's highly exothermic and it is an explosive reaction. So we want to keep the hydrogen and the chlorine away from each other. So we then design a tank. Okay, our tank is going to look something like this. Right? I'm just drawing it as a box. You've got, and there's a dozen of them in the book, different ways in the book. Here's the electrode number 1, and here's an electrode number 2. I'm not drawing them as fancy as the books, all right? And we connect them up to a plus and a minus and a plus and a minus, etc., like this. And we say you are plus side, you are minus side. Therefore, the Na plus is going to go this way, and the Cl minus and the OH minus are going to go that way, are they not? And at this side over here, I am going to get Cl2 gas given off, and on the opposite side over there, I am going to get H2 gas given off. This gas coming off here, I basically pipe away that way, and the chlorine gas coming out this side, I pipe away that way. All right? Now, the problem with this is that we've got to make sure that we keep these apart. This character over here, this OH minus, is a problem because the OH minus reacts with the carbon electrode. Most of the electrodes are carbon that we're going to be dealing with. Right? The carbon and the OH react. So what is we've got here is the carbon plus the OH minus, they actually react, which basically uses up the electrode quickly. It uses the electrode up very quickly. All right? Therefore, what we've got here, and just by the way, this forms HCl gas. So we're using up the electrode very, very quickly over here. So what do? We have to find ways around this, right? So what do? Is how do we circumvent these issues? Okay. That's what the chemical engineers, those of you doing this, are going to become chem eng. Wonderful. That's your job. You've got to find out, how do I do this stuff that the guys do in the lab? How do I do it on a big scale and it doesn't go boom? Right. So they've developed 3 different kinds of cell. A membrane cell. Number 2 is the mercury cell. Okay. And number 3 is going to be the diaphragm cell. All right. Now, generally speaking, the diaphragm cell has got asbestos. Meh, meh. This is phasing out. Okay, it causes asbestosis. This one, didn't even talk about it, it's got mercury, Hg, phase out. Although you'll see the mercury cell produces very high quality, okay, it has its problems with mercury. And as we know, certain countries, the pollution, the environmental agencies are not as strong as others. Therefore, I'm not saying it's tolerated, but definitely we do find leakage of mercury into the system. Mercury is a very, very difficult substance to control. So therefore, these would be phased out where possible in this situation and that situation. So I am going to look at the membrane cell currently. The others, do you know what? You can look at them in the textbooks, but they work the same way. The membrane cell, essentially we use something called brine in all of these. Brine is what we call a supersaturated salt solution. Okay? Those of you who've ever cooked something, you'll see that meats are very often injected with a brine solution. It's a preservative, it's got a salt in it, but it also keeps everything nice and sort of fresh and clean. The other side is seawater is briny, but the water that we're using here is really super saturated. So it's literally almost cloudy with salt, okay? And I was tempted to make a reference to a movie when I talked about cloudy, but I won't. Now, what does this thing look like? Brine is a supersaturated salt solution. So what do? We go back to, and we've got this box of ours over here. This is where I pump brine in. All right? Now, if I'm pumping it in, this is where brine out. Okay? This side, and in between, I have got a membrane. We'll get to him in a minute. All right? We'll get to him in a minute. This side, I pump water in. Okay? And out, I take NaOH. Where's that come from? Let's go back and look. Hello. NaOH comes from the OH. There. There. The NaOH comes from there. So what is happening is the water I'm pumping in over here, I do wish that it would work every time first time. The water I'm pumping in here is responsible for bringing the NaOH out over there. This over here is a membrane. Right. Over here on this side, I've got my 1 carbon. Let me say here, carbon electrode, like so. And I've got a charge over there. And on the other side, I've got another one. All right. This is also a carbon electrode over there and over this side. And what do I have? I have over here, I'll put in green. Over this side, over here, I take away the gas. And on this side, I remove hydrogen gas created by this electrode cathode over here. Cathode, which is negative. Now, remember, the OH was on this side. what is happening now is the OH is actually linking up with the Na plus, which is in here. But what happens, this is negative, so let's just see something. And I'm going to use red on the other side. This is positive. Okay, so the Na plus actually migrates through the membrane. But the membrane is ion exchange. Let me just make a note down over here and pull this down a wee bit just so that it's there for us to see. Make a note here. The membrane itself is an ion exchange membrane. Ion exchange membrane. It is ion selective. Which means the OH can't get through here. It allows the plus to get through, but not the minus. Right? That's what it's going to do. So the membrane is allowing the sodium to go through to combine with that because we want to get rid of the OH. Because the OH is going to mess up our anode, which is plus. Correct? Because what comes into that one is going to be my blue one is going to be my Cl minus up there when this is finished doing its thing. Okay, it's the Cl minus which is going that way. The OH minus, remember, wanted to go that way, but it can't. So the OH minus essentially is going to just be taken up with the Na plus because I'm allowing the Na plus to get through there. And that is basically the way that cell works with an ion selective membrane. Okay. Now, the next one that we're going to do is we're going to look at the, we're going to look at aluminium. And in the aluminium process, all right, we've got the same situation. You've got a big pot. The top roof of this thing is plus, and you've got electrodes hanging down into this huge pot over here. And in this case, we use molten. All right, here's our pot. Okay, let's take that down. And this outside piece over here that I'm drawing now is the negative. This is the positive side, and that's the negative side. So these are going to be plus over here, and this whole wall is going to be minus down here. Right? And what is this full of? This is the membranes, the thingies are made of graphite, which is carbon. All right, I'm just doing it exact. They're made of graphite, and they sit inside this pool, and I'm going to draw it in red, okay, of molten bauxite. Plus we add something called cryolite. Cryolite is there to reduce the melting temperature from 2000 degrees Celsius to 950 degrees Celsius, more or less. Okay. This is still a lot of energy required, so aluminium smelting is high energy. Okay. Usually countries with a relatively cheap supply of energy, and if you've got bauxite, you're pretty much A away, aren't you? Because if you've got a cheap energy and you've got bauxite, you can make aluminium pretty cheaply. So what happens in here then is the following, and I'm just going to go through it. You've got Al plus 3 electrons going to, remember this is equilibrium, Al solid. So basically the aluminium is going to be drawn to the negative, isn't it? And what's going to the other side? This is coming from aluminium oxide. All right, it's coming from bauxite, is basically Al2O3. So on the opposite side over here, on the green side, I've got O minus 2 going, correct? So what happens is I've got this oxygen. This is straightforward there. But on the positive side, all right, so that's fine. Oh, hang on, let's just see. This is gain, this is reduction, right? Reduction is happening. Therefore, reduction must be the cathode. Therefore, this is the cathode. Guys, it's the whole wall is lined like that. You get different varieties of these, obviously. I think it's called the Hall Herald cells. But essentially, we just need to know how it works in principle. They will probably give you a sketch and ask you to label which is which. So what have I got on the other side? Then at the anode, I've got this O2 going towards it. Right? So at the anode, I've got 6 O minus 2s going to 3 O2 plus 12 electrons. All right? This then, this is in a superheated, it actually joins, right, with the O2 and forms CO2. All right? Right? Well, the carbon joins with the O2. So you can see what is happening here. Therefore, we would balance it with that one there, and you'd have 3C plus 3O2 going to 3CO2. Where does that come from? Basically, carbon, oxygen. I've just balanced it out with the oxygens because I'm getting 3 oxygens from the plant itself. So that's just to balance it out. It's not critical if you don't get it at this stage. Really, it's not a big deal. I don't think I'm going to ask you the chemical. What they need to know is that this is the actual, this is the anode itself, which is a bummer because it means that the anode is used up. And worst of all, what are we getting? And let's put it in red, okay, because it's kind of horrible. And we get CO2, which is a greenhouse gas. So it uses a lot of electricity and it gives us CO2 given off. I mean, obviously, when they're doing these, the CO2 is taken out and dealt with in many. But yeah, a very expensive process. That is essentially the smelting of aluminium. And what do you need to know? How to label it, which is the anode, which is the cathode, which goes where. You can work it out. Why? Because you've got the aluminium ion in this molten mixture. And the aluminium is a positive ion, therefore it goes to the negative side. You don't need to memorize. All you need to know is that basic recipe and which is which. If it's in solution, it's an ion. Therefore, it's going to move to the electrode that it needs. Thank you very much for watching this. I hope that it's given a good sort of insight, a summary. They are intense. I've said before, we do go quickly, but you've got the advantage. You can stop, rewind, and work through with it and make the notes that I've made. Essentially, I've summarized probably about 5 textbooks to get to this. And yes, it's been an absolute pleasure doing it. And we're going to be adding in more infill videos as time marches on. But for the moment, that pretty much brings us to the end of one specific syllabus. Cheers. Thanks for watching again. Bye. Have a great one.